Hi class, we're going to continue talking about periodic trends. Now that we've talked about what they are, we want to provide explanations for the periodic trends, and you need to be able to do this. So going down a group from top to bottom, we know that as you go down, the atomic radius increases, the ionic radius increases, the ionization energy decreases, and the electronegativity decreases. But we want to explain why. Well, as you go down a group, the number of energy levels increases. This is because if you're looking at a periodic table, those numbered rows, horizontal rows, as you go from one row to the next, you are going to a higher energy level. So you get a new energy level every time you go down a row. So if we're going down within the same column, from the top to the bottom, you're getting more energy levels every time we go down. The distance between the nucleus and valence electrons will be greater because of that. When you think about energy levels, you can think about like layers on an onion or something like that. Every energy level is a new layer. So greater distance, and this is because of Coulomb's law, greater distance means that we have a weaker attraction between the nucleus and valence electrons. Again, you can think back to our example of using magnets. If you're holding magnets very close, you feel a strong attraction. If you're holding them at arm's length, there's very little or no attraction that you can actually tell, that you can actually notice. So then we have our explanations down here that tell us exactly why each of these trends is what it is. The atomic radius increases as you go down. Why is that? Well, we've increased the number of energy levels. The greater number of energy levels, the larger the atomic radius. And that makes sense because we're getting more layers to our atom. The ionic radius also increases. Again, the greater the number of energy levels, the larger the ionic radius. So that kind of makes sense. The ionization energy decreases. Now keep in mind when we talk about ionization energy and electronegativity, that's more directly related to the attraction between the nucleus and the valence electrons. So the reason that the ionization energy decreases is because we have a weaker attraction when there are more layers of electrons. And the same can be said for electronegativity. The weaker the attraction, the lower the ability of the atom to attract shared electrons in a bond. What if I'm going across a period from left to right? This is a little bit different. Now the atomic radius decreases going from left to right. Ionic radius decreases going from left to right. We're thinking about that snowman trend. The ionization energy, a snow cone trend, increases going from left to right, and electronegativity increases going from left to right. But let's think about the reason. As we go across the period, so across a period means I'm going from left to right, I would be within the same row. So I'm not changing energy levels. The number of energy levels stays the same. And if the number of energy levels stays the same, if you were to look back at that flow chart that we made, if the number of energy levels stays the same, we need to go on to our second thing that we compare. If the number of energy levels doesn't change, we compare the number of protons. And as you go across a period, the number of protons going from left to right, the number of protons is always going to increase. And if we have more protons, that means that we have a stronger attraction between the nucleus and valence electrons. That stronger attraction will pull the electrons towards the nucleus. So let's talk about atomic radius. Remember, the atomic radius is the distance from the nucleus to the outer layer of electrons. So if I have a stronger attraction, that nucleus is going to attract or pull those electrons in closer. The stronger the attraction, the smaller the atomic radius. Same exact explanation for the ionic radius, except we say ion instead of atom. The stronger the attraction, the smaller the ionic radius. Now, ionization energy is the amount of energy that we need to use to remove an electron. That's the amount of energy it takes to take an electron away. So that has to do with how strong the attraction is between the nucleus and the electrons. Not the distance, but the amount of attraction. Ionization energy increases because the stronger the attraction, the greater the energy that's required to remove an electron. And the electronegativity increases because the stronger the attraction, the greater the ability to attract shared electrons in a bond. Those are the forms of explanation that you need to be able to use in the practice that you're going to be doing today. The only thing that I wanted to do other than that in this video is just briefly summarize our trends and remind you of what they are. Okay, so our reasoning is the foundation. The number of energy levels increases as you go down a group, and as a result, the attractive force decreases. It's getting bigger, the attractive force decreases. The number of energy levels increases, that makes the radius increase, either radius, atomic or ionic. Okay. The attractive force decreases, which is why our ionization energy and electronegativity decrease. A couple important trends. Now, if I'm going across a period, we have to remember that the number of energy levels stays the same. That's a key point. We're in the same row, number of energy levels stays the same. But the number of protons increases, which causes the attractive force to increase. As a result, the atomic radius and ionic radius decrease. That attraction increases. That causes the radius to decrease. The electron cloud gets sucked in a little bit more. And the ionization energy and electronegativity increase. It becomes harder to take an electron away and more likely for the atom to attract new electrons to itself in a bond. That concludes the notes. I might do one more optional example problem video after this for you guys to look over, but you can probably handle the practice on your own at this point.